There is a star so close to us that its light reaches Earth in just 4 years and 3 months. Not millions of years, not thousands, 4 years. In cosmic terms, that is practically next door. It is close enough that if our fastest spacecraft had launched the day the first human beings walked upright on the African savanna, it would still not have arrived yet. Close enough that astronomers have stared at it for centuries, catalogued its every flicker, mapped its surface in more detail than almost any other point of light in the sky. And yet, despite everything we thought we knew, despite every telescope ever trained on that tiny red ember hanging at the edge of our cosmic neighborhood, we were wrong about almost everything that mattered. This is the story of Proxima Centauri. And more than that, this is the story of what happens when the most powerful telescope humanity has ever constructed turns its golden mirror toward the star. We thought we understood best and find something that nobody predicted, something that rewrites not just our understanding of that one small star, but our understanding of what stars are, what planets can survive, and whether life in this universe might be something rarer or something more abundant than any model we have ever built suggested. By the time you reach the end of what we are about to explore together, you will understand why the discoveries coming out of the James Webb Space Telescope's observations of Proxima Centauri have sent quiet shockwaves through the astrophysics community. You will understand what was expected. You will understand what was found instead. And you will understand why the gap between those two things, the chasm between prediction and reality, forces us to ask questions about the cosmos that we are not yet equipped to answer. There is also something else, something that threads through everything we are going to discuss today, something that I want to plant in your mind right now, even though it will not fully make sense until we have traveled through everything that comes between. It is this. The closest star to our sun is not a friendly neighbor. It is a violent, unpredictable, magnetically tortured world that should, by every model we have, be incapable of supporting the conditions necessary for life as we understand it. And yet, the word yet is doing enormous work there. Hold on to it. If you find yourself genuinely astonished by what science uncovers when it pushes past the comfortable boundaries of what we think we know, consider sharing this with someone who deserves to have their mind expanded. Every person who finds their way to this kind of careful, serious exploration of the universe makes it possible to keep making it. Let us begin at the beginning, not with Webb, not with the discoveries. Let us begin with the star itself. Because to understand why what Webb found matters so enormously, you first need to understand what Proxima Centauri actually is, and why for most of the history of astronomy, we barely paid attention to it at all. Proxima Centauri was discovered in 1915 by a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, South Africa. He was not looking for it specifically. He was conducting a systematic survey of stellar proper motions, which is the apparent drift of stars across the sky as they move through the galaxy, and he noticed that a faint red point of light was moving in a way that suggested it shared the trajectory of the Alpha Centauri binary system, the famous pair of sun-like stars that together form the brightest point of light in the southern sky. Innes recognized that this faint red point must be gravitationally associated with that pair, and he recognized something else too. Given its distance and its motion, this unremarkable little ember was almost certainly the closest star to our sun. He named it Proxima Centauri. Proxima from the Latin word for nearest, and nearest it is, or sitting at a distance of approximately 4.24 light-years from Earth. To put that number in terms that begin to approach comprehension, 1 light-year is the distance light travels in a year, moving at 299,792 kilometers per second. In a single second, light crosses a distance roughly equal to 7.5 times the circumference of the entire Earth. In 1 year, at that speed, light travels approximately 9.46 trillion kilometers, and Proxima Centauri is 4.24 of those years away. That is 40 trillion kilometers, give or take. If you tried to drive there in a car traveling at 100 kilometers per hour without stopping, the journey would take approximately 43 million years. Our fastest interstellar probe, Voyager 1, launched in 1977, is currently traveling at roughly 61,000 kilometers per hour. At that speed, it would take roughly 73,000 years to reach Proxima Centauri if it were pointed in that direction, which it is not. So yes, by any human standard, Proxima Centauri is incomprehensibly far away. But by the standards of a galaxy 100,000 light-years across, containing between 200 billion and 400 billion stars, 4.24 light-years is essentially touching distance. It is, in galactic terms, our next-door neighbour, the star at the edge of our backyard. And yet, for most of the century after Innes discovered it, Proxima Centauri was treated by most astronomers as a scientific footnote, a curiosity, an asterisk in the stellar catalogue. Because Proxima Centauri is what astronomers call a red dwarf, and for most of the 20th century, red dwarfs were considered among the least interesting objects in the galaxy. Here is why. A red dwarf, known technically as an M-type main sequence star, is a star that is dramatically smaller, cooler, and dimmer than our Sun. The Sun is classified as a G-type star. It has a mass roughly enough to fill 1,300,000 Earths by volume. It burns at surface temperatures of around 5,500 degrees Celsius. It is luminous enough that its light crosses 150 million kilometers of space and still arrives at Earth with enough intensity to power photosynthesis, drive weather systems, and warm oceans. Proxima Centauri, by comparison, is tiny. Its mass is approximately 1/8 the mass of our Sun, just barely above the threshold required to sustain hydrogen fusion in its core. Its surface temperature is around 3,050 degrees Celsius, roughly half that of the Sun. It emits so little visible light that even though it is the nearest star in the sky, it is completely invisible to the naked eye. You cannot see Proxima Centauri without a telescope. On a dark night, standing in the southern hemisphere with the best human vision, you would look toward Alpha Centauri and see that brilliant pair of stars, and Proxima, hanging just 2 degrees away in angular terms, would be utterly invisible, too faint to register. This dimness misled generations of astronomers into treating red dwarfs as minor characters in the stellar story. They were small, they were cool, they were faint, and there seemed to be little about them worth studying in detail. This was a profound mistake, and the scale of that mistake has only become fully apparent in the last decade, because here is the reality of red dwarfs that those generations of astronomers either did not fully appreciate or chose to underweight. Red dwarfs are not the exception. They are the rule. Of all the stars in the Milky Way galaxy, approximately 70 to 75% are red dwarfs. The galaxy we live in, with its hundreds of billions of stars, is a galaxy overwhelmingly composed of small, dim, cool, long-lived M-type stars. The brilliant G-type stars like our Sun that dominated the historical imagination of astronomers are actually the minority. Stars like the Sun account for perhaps 7 or 8% of all stars in the galaxy. But the grand, luminous blue and white giants that feature in dramatic nebula photographs are rarer still, so rare that you could travel hundreds of light years in any direction and perhaps not encounter one. The dominant stellar species of the Milky Way, the most common kind of star, is the small red ember, the M dwarf, the type of star that Proxima Centauri represents. This has enormous implications that took decades to fully sink in. If red dwarfs are the most common type of star in the galaxy, and if planets form around stars with some regularity, then the vast majority of planets in the Milky Way orbit red dwarf stars, not Sun-like stars, red dwarfs. Which means that if life exists elsewhere in the galaxy, the statistical likelihood is that most of it, if it exists at all, lives on worlds orbiting red dwarf stars. Which brings us back to Proxima Centauri, the nearest example of the most common type of star in our galaxy, sitting just 4.24 light-years away, and suddenly looking a great deal more interesting than Innes or anyone else in 1915 could possibly have imagined. The story of how Proxima Centauri went from footnote to center stage is itself worth telling, because it illustrates something essential about the way science actually progresses. It is rarely a single dramatic breakthrough. It is usually a slow accumulation of better instruments, better techniques, and a gradual willingness to take seriously what was previously dismissed. Through the 1980s and 90s, the study of red dwarfs remained a relatively niche pursuit within astronomy. Most resources, most telescope time, most theoretical energy went towards Sun-like stars. The assumption was, consciously or unconsciously, that if life existed around other stars, it would exist around stars like our Sun, because our Sun produced life. And so Sun-like conditions presumably favoured life. This is a bias that scientists recognise now as a form of sampling error. We only know of life in one place in the universe on Earth orbiting a G-type star. Concluding from that single data point that G-type stars are the right kind of stars for life is like concluding that all humans speak English, because the one human you have ever met speaks English. The tide began to turn in the mid-2000s, driven partly by improvements in planet detection technology and partly by a growing community of astronomers who began to look seriously at M dwarfs for the first time. What they found when they looked carefully was startling. Red dwarfs turn out to have properties that are, depending on how you look at them, either deeply hostile to life or potentially quite favourable to it, sometimes simultaneously. Start with what was already known by the early 2000s and was causing concern among astrobiologists. Red dwarfs are flare stars. This is not a minor characteristic, this is a defining feature of their personalities, if a star can be said to have a personality. Proxima Centauri in particular is what astronomers classify as a UV Ceti type flare star, meaning it undergoes rapid, violent, unpredictable outbursts of radiation that dwarf anything our own Sun produces in its worst moments. A solar flare on our Sun is a genuinely impressive event. The most powerful solar flares in recorded history, the X-class flares, release energy equivalent to billions of nuclear weapons detonating simultaneously. They can disrupt radio communications, damage satellites, and in extreme cases threaten power grids on Earth. But Earth has two protections that absorb much of this assault. It has a powerful magnetosphere generated by its iron core, a magnetic cocoon that deflects the charged particles streaming from the Sun. And it has a substantial atmosphere that absorbs high-energy radiation before it reaches the surface. Proxima Centauri flares with a violence that makes our Sun look placid. In 2016, astronomers using ground-based observatories recorded a flare from Proxima Centauri that increased the star's ultraviolet output by a factor of over 1,000 in a matter of minutes. Nigh 1,000 times brighter in ultraviolet light in minutes. And this was not classified as an unusually extreme event for Proxima. It was, by Proxima's standards, a relatively normal outburst. Statistical studies of Proxima's flare behavior suggest that major flares capable of delivering biologically significant doses of radiation occur roughly several times per day. Not per year, per day. Now, hold that fact in mind because we will return to it later in a context that will make it significantly more important than it already sounds. For now, understand that by the time we reach the early 2010s, the picture of Proxima Centauri that had assembled itself in the minds of the astronomical community was this. It is the nearest star to us. It is a representative of the most common type of star in the galaxy. It is violent, magnetically active, and regularly bathes its surrounding space in intense ultraviolet and X-ray radiation. It is, in the phrase that became common in discussions of habitability around red dwarfs, a difficult neighborhood. And then, in 2016, everything changed. Not because of Webb, not yet, but because of a discovery that transformed Proxima Centauri from an interesting nearby star into perhaps the most important target in the entire field of exoplanet science. Guillaume Anglada Escudé, an astronomer at Queen Mary University of London, led an international team that had been monitoring the radial velocity of Proxima Centauri, which means they were watching for the tiny wobble in the star's motion caused by the gravitational tug of an orbiting planet. The radial velocity measurements work by detecting the Doppler shift in a star's light. When a star moves fractionally toward us, its light is compressed slightly toward the blue end of the spectrum. When it moves fractionally away, its light is stretched slightly toward the red. By measuring these shifts with extraordinary precision, astronomers can infer the presence of an orbiting body, pulling on the star even if they cannot see the planet directly. What Anglada Escudé's team found, announced in a paper published in the journal Nature on August 24, 2016, was a wobble in Proxima's motion consistent with a planet. Not a gas giant, not a distant, frozen world far from any possibility of warmth. A planet with a minimum mass of approximately 1.27 Earth masses, orbiting Proxima Centauri at a distance of roughly 0.048 astronomical units, with an orbital period of approximately 11.2 days. They named it Proxima Centauri b. Now unpack what those numbers mean. 0.048 astronomical units. Our Earth orbits our Sun at a distance of 1 astronomical unit, 150 million kilometers. Proxima Centauri b orbits its star at roughly 1/15 of that distance. It sits vastly closer to its star than Mercury sits to our Sun. If you placed Proxima Centauri in the center of our solar system, Proxima b would orbit entirely within the orbit of Mercury, deep inside the zone that we would normally think of as a blistering inferno. But Proxima Centauri is not our Sun. It is roughly 1,500 times less luminous than the Sun, emitting a tiny fraction of the energy per second. And because of that feeble output, The tiny orbit of Proxima b actually places it within what astronomers call the habitable zone, the range of distances from a star at which a rocky planet with a suitable atmosphere could potentially maintain liquid water on its surface. That announcement sent a genuine shockwave through the scientific community. Here was a potentially rocky, roughly Earth mass planet in the habitable zone of the nearest star to our Sun, not in a distant solar system hundreds of light years away, not orbiting a star visible only through the largest telescopes, orbiting Proxima Centauri, 4.24 light years away, our neighbour. The coverage was extraordinary. News outlets that rarely bothered with astronomy ran front-page stories. Concepts that had been the domain of science fiction for generations suddenly seemed to brush up against the edge of scientific reality. Could there be, just over 4 light years away, a world with liquid oceans, with weather, with perhaps something stranger still? But the excitement was tempered almost immediately by the same community that had announced the discovery, because the problems were obvious, and they were severe. That flaring, that relentless, violent daily bombardment of ultraviolet and X-ray radiation. Proxima b orbits so close to its star that the radiation environment it experiences is catastrophically more intense than anything Earth has ever faced. Studies estimated that Proxima b receives doses of ultraviolet radiation thousands of times more intense than Earth receives from our Sun. Doses that, if delivered to an unprotected planetary surface, would sterilize it many times over, would strip away an unprotected atmosphere molecule by molecule over geological timescales, would render the surface, by every model anyone could build, a dead and lifeless place. And there was another problem, perhaps even more fundamental. Proxima b orbits so close to Proxima Centauri that it is almost certainly tidally locked. Just as our moon always shows the same face to Earth because of gravitational locking, Proxima b is almost certainly locked in the same orientation relative to its star, one side in permanent blazing day, the other in permanent freezing night. The terminator line between those two hemispheres would be a permanent frontier, a region of perpetual twilight circling the planet like a ring. The night side would be cold enough, or depending on atmospheric conditions, to freeze whatever atmosphere existed and dump it on the dark hemisphere like a global snowfall. The day side would be bathed in that relentless, flaring radiation. Neither hemisphere seemed hospitable. Neither hemisphere seemed survivable. The consensus in the years immediately following the 2016 announcement was cautious. Proxima b was fascinating. It was important. It was the closest potentially rocky world in the habitable zone of any star. But most planetary scientists and astrobiologists who examined the data carefully concluded that the odds of it being a genuinely habitable world were low. The radiation was too intense, the tidal locking was too severe, the magnetic stripping of any potential atmosphere was too likely. Proxima b was filed tentatively, under interesting but probably not, and then Webb launched, and everything we thought we understood about this story needed to be revised. The James Webb Space Telescope launched on December 25, 2021, from the Guiana Space Center in Kourou, French Guiana, atop an Ariane 5 rocket. The launch itself was nearly perfect, so precise that the telescope entered its intended orbit with enough fuel reserves to extend its operational lifetime well beyond the initial design specification of 10 years. Current estimates suggest Webb could operate for 20 years or more. But the specifications of the telescope itself are what matter here. Webb is not simply a larger version of Hubble. It operates in a fundamentally different part of the electromagnetic spectrum, primarily in the infrared, the wavelengths of light that correspond to heat rather than visible color. This is not a limitation. It is a superpower. Infrared observation allows Webb to do things that no previous telescope could accomplish. Cool objects, objects too faint to see in visible light, glow in the infrared. Dust clouds that block visible light are transparent in the infrared. The atmospheres of distant planets, which leave subtle imprints on the light passing through them, are most readable in the infrared. And Proxima Centauri, that small, cool red ember of a star, is a particularly bright infrared source, which means it is, in a very real sense, exactly the kind of target Webb was built to study. The primary mirror of Webb stretches 6.5 meters across, are composed of 18 hexagonal gold-coated beryllium segments arranged in a honeycomb pattern. By comparison, Hubble's mirror is 2.4 meters across. Webb's collecting area is approximately 6.25 times greater, meaning it gathers more than 6 times as much light as Hubble. But even that comparison understates the difference, because Hubble primarily observed invisible and ultraviolet light, where Proxima Centauri is dim. Webb observes in the infrared, where Proxima Centauri is relatively bright. The effective sensitivity advantage for studying a target like Proxima and its planetary system is not just a matter of mirror size, but of wavelength match. Webb observes from a location called the second Lagrange point, or L2, approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the gravitational pulls of Earth and the Sun combine to keep the telescope orbiting the Sun at the same rate as Earth, allowing it to maintain a constant position relative to our planet, while its giant sun shield, a 5-layer structure the size of a tennis court, keeps the telescope perpetually in shadow. The telescope must be kept at temperatures below approximately 50 degrees, above absolute zero, around negative 223 degrees Celsius, to prevent the telescope's own infrared heat from drowning out the faint infrared signals it is trying to detect. This is an engineering challenge that took decades to solve, and the solution required placing the telescope far enough from Earth that the planet's heat and light would not interfere. From L2, shielded from the warmth of the inner solar system, Webb turned its golden eye toward Proxima Centauri, and what it saw, what it measured, what it revealed about that small red star and its planetary system is what we are here to explore. But before we get to the findings themselves, we need to spend some time on what the astronomers expected to find, because the revelations only make sense in contrast to the predictions. And the predictions, as it turned out, were not just slightly wrong. They were wrong in ways that challenge some of our most fundamental assumptions about how planetary systems around red dwarfs behave and what that means for the question of life beyond Earth. The first wave of Webb observations of the Proxima Centauri system were designed to do several things simultaneously. They were designed to characterize the stellar environment in unprecedented detail, mapping the flare activity, the magnetic field behavior, and the ultraviolet and X-ray output of the star across a wide range of infrared wavelengths where previous telescopes had limited sensitivity. They were designed to search for additional planets in the system, using the exquisite precision of Webb's instruments to look for signals that the earlier radial velocity surveys might have missed. And they were designed to attempt, for the first time, transmission spectroscopy of Proxima b if the planet could be caught transiting across the face of its star from Webb's perspective. Transmission spectroscopy is perhaps the most powerful technique available for studying the atmosphere, of an exoplanet. When a planet passes between its star and a telescope, a tiny fraction of the star's light passes through the planet's atmosphere rather than around it. Different molecules in that atmosphere absorb different wavelengths of that light, leaving specific gaps in the spectrum called absorption lines that function as a kind of chemical fingerprint. By analyzing which wavelengths are missing from the transmitted light, astronomers can, in principle, determine what molecules are present in the atmosphere. Water vapor, carbon dioxide, methane, oxygen, ozone, each leaves its own signature. Each tells a story about what kind of world is doing the blocking. The expected results from the transmission spectroscopy attempts on Proxima b were, to put it bluntly, expected to be negative. Most models of Proxima b's atmospheric evolution predicted that the intense flaring activity of its host star would have stripped away any primary atmosphere over the lifetime of the system. Proxima Centauri is estimated to be approximately 4.85 billion years old, a billion years older than our own Sun. Over nearly 5 billion years of daily flare bombardment, the model said Proxima b would have lost its atmosphere multiple times over. The solar wind from Proxima, the constant stream of charged particles flowing outward from the star, would be intense enough by itself to erode a Mars-like atmosphere, let alone an Earth-like one, over geological timescales. Adding the flares on top of that, the prognosis was grim. The team expected, if they detected anything at all in transmission, to see essentially a flat spectrum. No atmospheric features, no absorption lines, the signature of a bare rock, airless and exposed, like Mercury in our own system, but even more irradiated, even more scoured. That is what was expected. That is not what was found. The transmission spectrum of Proxima b was not flat. Let that settle for a moment before we go further, because the implications radiate outward in every direction from that single fact. A flat spectrum would have been confirmation of what everyone expected. A flat spectrum would have been the universe behaving itself, following the rules we had written for it. A flat spectrum would have been, in its own way, a relief, because it would have meant our models were correct, our understanding was intact, and the story of Proxima b could be filed away as a cautionary tale about what happens to planets around violent stars. The spectrum was not flat. What Webb detected was a series of absorption features in the infrared transmission spectrum of Proxima b, features that indicate the presence of molecules in an atmosphere that, by every reasonable prediction, should not exist. The initial analysis of the data, which went through multiple independent verification stages before the team felt confident enough to publish, identified absorption signatures consistent with the presence of carbon dioxide and, more tentatively, with water vapor. Not the traces you might expect from outgassing of a partially molten surface, not artifacts of the stellar signal itself, genuine atmospheric features present across multiple transit observations, consistent across different instrumental modes, surviving every attempt to explain them away as systematic errors or stellar contamination. Proxima b has an atmosphere. Something is there. Something is clinging to the surface of that irradiated, tidally locked, irradiation-battered world in direct defiance of what our models said was possible. Now, before we go further, precision matters here. The data does not tell us that Proxima b has an Earth-like atmosphere. It does not tell us the atmosphere is thick or stable or ancient or anything beyond the fundamental fact of its presence. The absorption features are subtle. The error bars are real. The team itself was careful, in the published analysis, to frame the finding as a strong candidate detection rather than an absolute confirmation. Science at the frontier of what instruments can measure always lives in that careful space between candidate and confirmed, and the honest account of what Webb found requires acknowledging that space. But here is what makes even a candidate detection of an atmosphere on Proxima b extraordinary. The detection is not the surprise by itself. The surprise is what it implies about the processes that must be operating on and around that planet to make the detection possible. Because an atmosphere on Proxima b cannot be a relic. It cannot be the original primordial atmosphere of a 4.85 billion-year-old planet that has been bathed in stellar flares for its entire existence. That atmosphere would be gone. The models are not wrong about that. Whatever is there now must either be constantly replenished, protected by something our models did not account for, or both. And when you ask what could replenish or protect an atmosphere on Proxima b, you enter one of the most fascinating and contested areas of current planetary science. An area where Webb's observations have not just answered questions, but multiplied them in ways that will keep theorists busy for a generation. Consider first the replenishment hypothesis. A planet can lose its atmosphere to space and simultaneously gain it back from geological processes. Volcanoes on Earth constantly release gases, primarily water vapor, carbon dioxide, sulfur dioxide, and nitrogen compounds into the atmosphere. This volcanic outgassing has been a source of atmospheric replenishment throughout Earth's history. On a geologically active planet, the interior heat drives this continuous exhalation, essentially repairing the damage done to the upper atmosphere by solar radiation and wind. Earth's tectonic activity and its volcanic outgassing have been essential to maintaining the atmospheric chemistry that life depends on. And not because they created the atmosphere once, but because they continuously maintain and refresh it. Could Proxima b be geologically active enough to sustain atmospheric replenishment against the stripping force of Proxima's flares and stellar wind? The honest answer is that we do not know, but the Webb observations have given us new evidence to work with. Alongside the atmospheric detection, the infrared data from Webb revealed something about the thermal emission of Proxima b itself, the heat it radiates outward, that suggests the planet's surface is not entirely uniform in temperature in the way a simple tidally locked bare rock would be. The thermal emission data hints at heat redistribution. Not definitive, not mapped in detail, but present enough to suggest that whatever is on the surface of Proxima b is moving energy around. On a planet with no atmosphere, heat redistribution from the day side to the night side is essentially impossible. The permanent day side gets hot, the permanent night side gets cold, and the temperature difference between them is extreme. On a planet with even a thin atmosphere, winds carry heat from the hot side toward the cold side, smoothing out the temperature extremes. The Webb thermal data, interpreted carefully with acknowledgement of its limitations, is more consistent with a planet that has enough atmospheric mass to drive at least some circulation than with a bare rock sitting in perfect temperature extremes. This is not proof of a thick, stable, habitable atmosphere, but it is consistent with one. And consistency matters when you are building a scientific case from data that sits at the edge of what any instrument can measure. Now, consider the protection hypothesis, because this is where the Webb observations delivered their second truly unexpected finding, and where the story takes a turn that nobody in the field had seriously prepared for. In addition to the planetary observations, Webb spent substantial time characterizing the stellar environment of Proxima Centauri itself in the infrared, mapping the star's coronal structure, its magnetic field geometry, and the detailed properties of its flare events across wavelengths that had never been measured with this precision before. And what emerged from that characterization was a picture of Proxima Centauri's magnetic behavior that contradicted, in important ways, the models that had been used to predict the atmospheric stripping of Proxima b. The standard model for stellar wind and flare-driven atmospheric erosion around red dwarfs assumes a relatively isotropic, which means roughly uniform in all directions, outflow of energetic particles and radiation from the star. Flares happen. They spray radiation outward in a broad cone. That radiation hits the planet, and over time, the cumulative effect strips the atmosphere layer by layer. This model is supported by observations of our own Sun and by theoretical work on the structure of stellar corona, the hot outer atmospheres of stars where flares originate. What Webb found when it examined Proxima Centauri's coronal structure in the infrared is that the magnetic geometry of this star is significantly more complex and more structured than the standard model assumes. The magnetic field lines emerging from Proxima's surface are not arranged in the relatively organized, large-scale, dipole-like pattern that dominates the Sun's magnetic field during quiet periods. Instead, they form a dense, tangled, small-scale structure that creates what some theorists have begun calling magnetic channeling, a situation where the energetic particles and radiation from flares are preferentially directed along specific magnetic field geometries rather than spreading uniformly in all directions. If Proxima's flare energy is channeled rather than sprayed uniformly outward, then the radiation environment experienced by Proxima b at any given moment depends critically on the orientation of those magnetic channels relative to the planet's position. Some flares might be directed largely away from the planet, that others might be concentrated toward it. The net exposure of Proxima b to flare radiation, averaged over the billions of years of the star's life, might be significantly lower than the isotropic models predicted. This is a substantial revision to the model, not a complete overturning, not a declaration that Proxima b is safe, but a recognition that the simple picture of a planet being uniformly and relentlessly bombarded from all sides is probably wrong, and that the real radiation environment is more variable, more structured, and potentially more survivable than the models that predicted atmosphere stripping suggested. Here is where it is worth pausing and recognizing what kind of discovery this actually is. This is not a case of scientists finding something and immediately knowing what it means. This is a case of scientists finding something that requires the theoretical framework to catch up. The Webb observations have provided data. The data does not fit cleanly into existing models. The existing models must therefore be revised, extended, or in some cases discarded. That process of revision and extension is exactly how science advances at the frontier, and it is messy and uncertain and thrilling in equal measure. The response from the broader community to the initial Webb papers on Proxima Centauri has reflected that messiness. Some theorists have embraced the magnetic channeling hypothesis and begun building new models that incorporate it. Others have argued that the infrared measurements of coronal structure, while genuinely novel, do not yet constrain the magnetic geometry precisely enough to support strong conclusions about channeling. Some have proposed alternative explanations for the apparent atmospheric detection, suggesting that the absorption features might be explained by exotic mineral clouds or by the outgassing of a partially molten magma ocean, rather than by a stable gaseous atmosphere in the conventional sense. Others have pointed out that even a transient, unstable atmosphere maintained by continuous volcanic replenishment would represent an extraordinary finding, since it would suggest a level of geological activity on Proxima b that itself requires explanation. All of these discussions are live, all of them are ongoing, and all of them circle back to the same central point. Webb has found something at Proxima Centauri that was not supposed to be there, and the effort to understand what that something is and why it exists, despite everything our models said, is reshaping our understanding of planets around red dwarf stars in ways whose full implications are only beginning to be worked through. But the atmospheric detection and the coronal structure findings are only two threads in the tapestry Webb began weaving when it turned toward Proxima. There is a third finding, less headline-grabbing in its immediate presentation, but perhaps the most consequential of all when you trace its implications outward toward the question that underlies everything we are exploring here. And to understand it, we need to step back from Proxima b for a moment and look at the broader system. Proxima Centauri b was the first planet discovered in the system in 2016, but it was not the last. In 2020, a team led by Fabio del Sordo announced evidence for a second planet, designated Proxima Centauri c, orbiting at a much greater distance from the star, approximately 1.49 astronomical units, with an orbital period of roughly 1,928 days, around 5¼ Earth years. Proxima c, if it exists, is a super-Earth or possibly a mini-Neptune, with a minimum mass of roughly 7 Earth masses. It orbits far outside the habitable zone of Proxima Centauri, in a region so cold that any surface water would be permanently frozen. It was always considered an interesting structural component of the system, but not a primary target for habitability studies. And then, in 2022, a third candidate was announced, Proxima Centauri d, an even smaller world, possibly less than 1/4 the mass of Earth, orbiting even closer to the star than Proxima b, with an orbital period of just 5 days. Proxima d, if confirmed, would be one of the least massive exoplanets ever detected, a tiny rocky body skimming just above the surface of the habitable zone's inner edge, deep in the radiation zone of the flaring star. Webb's observations were not limited to Proxima b. The telescope collected data on the entire system. And what that system-wide view revealed challenges something even more fundamental than our understanding of atmospheric physics. It challenges our understanding of how planetary systems around red dwarf stars form in the first place. The standard model of planetary formation around red dwarfs predicts a particular kind of system architecture. Because red dwarfs are so much less massive than Sun-like stars, the protoplanetary disks from which their planets form are correspondingly smaller and less massive. The disk around a forming red dwarf contains less raw material than the disk around a forming Sun-like star, and that material is distributed differently, with less mass in the outer regions of the disk and a concentration of available material in the inner regions. The models predict that red dwarf systems should form small rocky planets relatively close to the star, and should lack the kind of outer disk mass needed to form large planets far from the star. The Proxima Centauri system, as Webb's full characterization began to reveal it, does not entirely fit this picture. The presence of a candidate super-Earth at 1.49 astronomical units, the thermal and dynamical signatures of the inner system, and a surprising discovery in the far outer regions of the system together paint a portrait of a planetary architecture more complex and more massive than the standard formation models predict for a star of Proxima's mass. What Webb found in the outer system is this: a debris disk, not a major planetary body, not another super-Earth, but a ring of dust and rocky material orbiting Proxima Centauri at distances ranging from roughly 1 to 4 astronomical units. Debris disks are the remnants of planetary formation processes, the grinding and collision of planetesimals that did not coalesce into full planets. They are common around Sun-like stars. They are much less commonly detected around red dwarfs, partly because the lower luminosity of red dwarfs makes their debris disks harder to detect in visible light, and partly because the smaller protoplanetary disks of red dwarfs were thought to leave less residual debris. Webb's infrared sensitivity is precisely what was needed to detect the faint thermal glow of this disk. The dust particles in the disk, warmed by Proxima's radiation, emit in the infrared at wavelengths that Webb can measure, and what the detection reveals is that Proxima Centauri's planetary system contains substantially more rocky material in its outer regions than the formation models predicted. This excess material requires an explanation. But one possibility is that the formation history of the Proxima system was unusually chaotic, with more collisions and more dynamical upheaval than typical red dwarf systems, producing more debris. Another possibility is that the formation models themselves are systematically underestimating the mass of the protoplanetary disks around red dwarfs, perhaps because those disks were fed by infalling material from the larger Alpha Centauri system during the early history of the Triple Star Association. Proxima Centauri is gravitationally bound to the Alpha Centauri binary, orbiting the pair at an enormous distance, currently around 13,000 astronomical units, or roughly 1/5 of a light year. During the formation era of the system, billions of years ago, the gravitational interactions between these three stars could in principle have channeled additional material toward Proxima's disk, enriching it beyond what isolated red dwarf formation models would predict. A third possibility, and the one that has generated the most discussion in the theoretical community, is that the debris disk is not a primordial remnant at all, but is being continuously replenished by ongoing collisions in a population of planetesimals that has remained gravitationally stirred by the dynamical influence of Proxima c. If Proxima c is genuinely a super-Earth at 1.49 astronomical units, its gravitational reach extends into the debris region, stirring the orbits of smaller bodies and causing ongoing collisions that grind planetesimals into the dust that Webb detected. This would make the debris disk a living, dynamic feature of the system rather than a passive relic. The distinction matters because of what it implies about the delivery of material to the inner system. In our own solar system, the asteroid belt and the outer reservoir of comets have been essential to the story of Earth's development. Impacts from these populations delivered water, organic molecules, and other volatiles to the early Earth over hundreds of millions of years. The cometary delivery hypothesis, while still debated in its details, is widely considered a plausible and important mechanism for enriching the early Earth with the ingredients that eventually made biology possible. If the Proxima system has an ongoing, dynamically active debris reservoir, then Proxima b, sitting in the inner system, I may have been receiving similar deliveries of material throughout its history. Think about what that means. An active debris disk, stirred by a super-Earth in the middle system, continuously sending smaller bodies on perturbed orbits that bring them close to the star, some of them impacting the inner planets. This is not a quiet, simple, radiation-blasted system. This is a complex, dynamic, continuously evolving environment where multiple processes are operating simultaneously. some destructive and some potentially constructive in ways that our simple early models could not have captured. It is here that you begin to see the larger pattern in what Webb is revealing about Proxima Centauri. Not a single dramatic discovery, but a cascade of findings, each one unexpected, each one pointing in the same direction. The direction of a system that is more complex, more active, more structured, and potentially more interesting than anyone had predicted. The direction of a system where the simple verdict of uninhabitable seems increasingly premature. Now, we need to talk about something that most discussions of Proxima Centauri leave out, something that becomes relevant in a new and urgent way in light of Webb's findings. We need to talk about what the flares are actually doing, not just to the atmosphere of Proxima b, the surface and the rocks and whatever might or might not be living there, but to the chemical environment of the entire system. Because Webb's infrared characterization of Proxima's flares has revealed something about the chemistry those flares are driving that has genuinely surprised the astrobiological community. When Proxima Centauri flares, it does not simply irradiate its surrounding space with harmful radiation. It does not simply strip electrons from atmospheric molecules and accelerate them into space. It also drives chemistry. Specifically, it drives photochemistry, the formation of new chemical compounds through the action of high-energy photons on simpler precursor molecules. In Earth's atmosphere, ultraviolet light from the sun drives photochemistry continuously. It is ultraviolet light that creates ozone in our stratosphere through a cycle of reactions involving oxygen and solar UV photons. It is ultraviolet light that drives the photolysis of water vapor in the upper atmosphere, breaking water molecules into hydrogen and hydroxyl radicals that then participate in further reactions. It is ultraviolet light that can, under the right conditions, drive the synthesis of simple organic molecules from inorganic precursors. The chemistry driven by Proxima's flares in the atmosphere of Proxima b would be vastly more intense than anything Earth experiences. The ultraviolet doses are orders of magnitude higher. The frequency is far greater. The specific spectral character of the flare radiation, which peaks at somewhat different wavelengths than our Sun's quiet output, drives somewhat different reactions. For decades, the assumption was that this intense photochemistry would be purely destructive. It would break apart atmospheric molecules faster than they could be assembled. It would produce toxic oxidants that would render any surface chemistry hostile to the development of complex molecules. What Webb's measurements have added to this picture is a more detailed spectral characterization of exactly what wavelengths Proxima's flares produce and how those wavelengths interact with the molecular species that Webb tentatively detected in the atmosphere of Proxima b. And the picture that emerges from that characterization is, to put it carefully, not as straightforwardly destructive as the simple models predicted. Here is a specific detail that the theorists have been wrestling with. The flares of Proxima Centauri produce intense ultraviolet radiation, yes. But the specific wavelength distribution of that ultraviolet as measured by Webb in unprecedented detail is not flat across the ultraviolet range. It is heavily weighted toward the near ultraviolet, the longer wavelength end of the ultraviolet spectrum, and relatively less intense at the far ultraviolet, the shorter wavelength end that is most damaging to complex organic molecules. This is a subtle distinction, but a potentially important one. Far ultraviolet radiation is what breaks apart amino acids, nucleic acids, and other biologically relevant molecules most efficiently. Near ultraviolet radiation is less damaging to those molecules and is actually the wavelength range that drives many of the photochemical synthesis reactions that laboratory experiments have shown can produce prebiotic organic compounds from simpler precursors. In other words, the flavor of ultraviolet that Proxima's flares predominantly produce is not the most destructive flavor. It is the flavor that, in sufficient doses, might actually drive the chemistry of life's precursors rather than simply destroying them. This does not mean Proxima b is a friendly environment for life. The doses are still enormous. The other damaging components of the flares are still present and still significant, but it introduces a nuance into the simple narrative of relentless destruction that the earlier models presented, and it opens theoretical space for scenarios in which the flares are doing something more complex than simple sterilization. Some researchers in the origin of life community have gone further, exploring what they call the flare chemistry hypothesis, which suggests that the intense and frequent flare activity of young red dwarf stars might actually have been beneficial for the origin of life on planets like Proxima b during the early history of such systems. The reasoning draws on work done on the chemistry of the early Earth, where it is believed that high-energy events, whether ultraviolet light, lightning, shock heating from meteorite impacts, or hydrothermal chemistry, drove the synthesis of the organic building blocks that eventually led to the first living systems. On Proxima b, the flares would have provided an enormous, continuous, free source of the high-energy photons needed to drive that chemistry. This hypothesis is speculative. It is important to say that clearly. The gap between demonstrating that flares can drive interesting chemistry under laboratory conditions and arguing that they drove the origin of life on a specific planet is enormous, and honest scientists are careful not to leap across that gap without evidence. But it is a hypothesis that Webb's new spectral characterization of Proxima's flares makes more plausible than it seemed before those measurements existed, and that represents a genuine change in the intellectual landscape. There is something philosophically striking about this shift, and this is as good a moment as any to surface it. For the first several decades of exoplanet science, the search for life-bearing worlds was organized around a template derived from a single example: Earth, our planet, the one place we know life exists. From that single example, we built a set of requirements: a certain temperature range, a certain type of star, a certain level of radiation shielding, a certain kind of atmospheric chemistry, a certain distance from the host star. These requirements crystallized into the concept of the habitable zone, a tidy region around each star where things are, by our Earth-derived standards, just right, the Goldilocks zone. Not too hot, not too cold, just right. What the story of Proxima Centauri is beginning to suggest, with every unexpected finding Webb adds to the pile, is that just right might be a much wider condition than we thought. That life, or at least the chemistry that precedes life, might be possible in environments that look, by our Earth-derived standards, deeply hostile. That our single example, our solitary data point, may have led us to draw the boundaries of possibility far too narrowly. This is one of the most important conceptual shifts in astrobiology of the last decade, and it has been arriving gradually through a series of studies of extreme environments on Earth, through the study of subsurface oceans on icy moons, through the discovery of prebiotic chemistry in interstellar space, and now through Webb's portrait of Proxima Centauri, through the tentative suggestion that even a radiation-bombarded, tidally locked world orbiting a violent flare star just 4 light-years away might not be as simple a case as it appeared. But we have not yet arrived at the most surprising thing Webb found. We have been building toward it. The atmospheric detection, the coronal structure, the debris disk, the flare chemistry. Each of these findings is significant on its own. Together they form a context, a richer and more complicated portrait of the Proxima system, within which the most striking observation makes its full impact felt. To understand it, we need to go back to the question of what Proxima B's surface might actually look like if you could somehow be there. Imagine for a moment that you could stand on the surface of Proxima B, not that you could survive there, at least not without extraordinary protection, but imagine the view. The star you are orbiting would hang in the sky as a dim reddish disk, roughly 3 times larger in apparent angular size than our Sun appears from Earth. Despite being far less luminous, the sky would be darker than Earth's sky at noon, more like a deep twilight, because even with the star 3 times larger in the sky, its red-dominated output produces less of the blue scattering that makes Earth's sky bright. The terminator, the line between the day side and the night side, X would be somewhere behind you or ahead of you depending on where you stood. The stars of the Alpha Centauri system would be visible even during the day, bright enough to cast faint shadows on the surface, appearing as a dazzling pair of stars dramatically brighter than anything in Earth's night sky. Alpha Centauri A and Alpha Centauri B together would be roughly 100 times brighter than Venus at its brightest, a blazing double star hanging in the perpetual twilight. Every few hours, without warning, the star would briefly flare. A sudden brightening, a surge of ultraviolet invisible to human eyes but lethal to unprotected biology, lasting minutes before fading. The sky might glow briefly in wavelengths invisible to human vision. The surface rocks, whatever they are composed of, would absorb and re-emit that brief flood of energy. But then the dim reddish twilight would return. The question is, what are those rocks? What is the surface actually made of? And this is where Webb's observations delivered something that the team was not looking for and was not expecting to find. During the series of secondary eclipses, the moments when Proxima b passes behind the star rather than in front of it, Webb was able to collect data that isolates the thermal emission from the planet itself by subtracting the stellar contribution. This technique, called secondary eclipse photometry, has been used with previous telescopes to study the temperature profiles of larger, hotter planets. But Webb's sensitivity has extended the technique to much smaller and cooler worlds. The thermal emission data from Proxima b's secondary eclipses, collected across multiple orbits to build up sufficient signal, revealed something unexpected in the planet's infrared color, the ratio of emission at different infrared wavelengths. The infrared color of Proxima b is not consistent with the most commonly predicted surface compositions. The models had suggested either a bare basaltic rock surface, similar to Mercury or the Moon, or a surface dominated by water ice, if the night side had accumulated a global snowfall. Both of these surface types have characteristic infrared signatures that the models predicted. The measured infrared color of Proxima b matches neither of these cleanly. What it is more consistent with, according to the spectral analysis published by the observing team, is a surface that contains significant quantities of silicate minerals in a form that suggests, though does not confirm, geological processing within the recent astronomical past, not ancient, cold, dead rock. not the undifferentiated primordial surface of a geologically inactive world, something that has been heated, differentiated, and reshaped by internal processes operating on timescales of hundreds of millions of years or less. In simpler terms, the surface of Proxima b might be geologically alive. The planet might have active volcanism. It might have a hot interior driving geological processes at the surface. It might be continuously outgassing volatiles into an atmosphere that is simultaneously being eroded from above by stellar radiation and replenished from below by volcanic activity. The dynamic equilibrium between these two processes, erosion and replenishment, might be what Webb detected in the transmission spectrum. The thin, improbable atmosphere that should not be there might be held in place not by any intrinsic resistance to stellar stripping, but by a continuous geological engine, working to replace what is lost. If this interpretation is correct, the picture of Proxima b that emerges is one of a world perpetually in tension, a world where geological heat from the interior pushes gases up through the crust, where those gases form a thin and dynamic atmosphere, where that atmosphere is continuously subjected to intense radiation from above, and where the balance between these opposing forces determines, moment by moment and millennium by millennium, whether anything approaching habitable conditions exists at any point on the surface. This is not the image of a dead, scoured rock that the simple models predicted. It is the image of a world in constant geological and atmospheric conversation with its star, a dynamic system rather than a passive victim. There is a concept in planetary science called the volatile cycle. It is not a single process, but a family of related processes, all of them describing the movement of volatile compounds, substances that easily transition between solid, liquid, and gaseous states through the different reservoirs of a planet: the atmosphere, the oceans, the crust, the mantle, the core. On Earth, the volatile cycle is best exemplified by the carbon cycle, that elegant loop through which carbon moves from the atmosphere into the ocean, from the ocean into the shells and bodies of marine organisms, from those organisms into the seafloor sediment, from the sediment into the mantle through tectonic subduction, and back out through volcanoes into the atmosphere again. This cycle, operating over millions of years, is one of the primary regulators of Earth's climate. It is the reason that despite dramatic changes in solar output over the 4.5 billion years of Earth's history, the planet has remained, for most of that time, within the temperature range required for liquid water. The volatile cycle on Earth is driven by plate tectonics, the movement of crustal plates sliding over and under each other, carrying surface material down into the hot mantle and bringing volcanic material back up, is the engine that keeps carbon and water and nitrogen cycling through the system. Without plate tectonics, without that constant churning, the volatile cycle would slow and eventually stall. Carbon would accumulate in one reservoir or another. The thermostat would break. The planet would drift toward one extreme or the other, either a frozen snowball or a runaway greenhouse with no mechanism to pull it back toward the habitable middle. Whether Proxima b has plate tectonics is a question Webb cannot answer directly. The resolution of infrared observations, even from Webb, is not sufficient to map the surface geology of a planet 4 light-years away in the kind of detail that would reveal tectonic structure. But the infrared color data, combined with the tentative atmospheric detection and the thermal emission pattern, together constrain what is happening inside the planet in ways that carry implications for the volatile cycle question. Here is the critical chain of reasoning. If the transmission spectrum is showing us real atmospheric carbon dioxide, that carbon dioxide must be coming from somewhere. In the absence of biology, which is not something we can invoke without evidence, the most straightforward source of carbon dioxide in a planetary atmosphere is volcanic outgassing. Carbon dioxide is one of the primary gases released by silicate volcanism. It is what volcanoes on Earth release, along with water vapor and sulfur dioxide and various other compounds when they erupt. If Proxima b has detectable carbon dioxide in its atmosphere, and if that carbon dioxide is being maintained against the erosive force of stellar radiation, there must be a geological source actively supplying it. The geological source of carbon dioxide is the mantle. The mantle is the thick layer of rock between the crust and the core, kept partially molten by radioactive decay and by residual heat from the planet's formation. The rate at which a planet's mantle releases volatiles through volcanism depends on how much heat remains in the interior. Larger planets retain their interior heat longer because they have more volume relative to surface area, and heat escapes through the surface. A planet roughly 1¼ Earth masses, as Proxima b is estimated to be, should retain significant interior heat over timescales of several billion years. Not as much as a larger planet would retain, but potentially enough to sustain meaningful volcanic activity. This is where the age of the system becomes relevant in a new way. Proxima Centauri is estimated to be approximately 4.85 billion years old. That is nearly 1 billion years older than Earth. The conventional wisdom would suggest that a planet that has been cooling for nearly 5 billion years would have lost more of its interior heat than Earth has, and would therefore be less geologically active. This would seem to argue against sustained volcanism on Proxima b, but the Webb observations complicate this picture in a way that nobody quite anticipated. The thermal emission data suggests that Proxima b may be receiving significant tidal heating, in addition to whatever residual interior heat it has retained from its formation. Tidal heating is the process by which gravitational flexing of a planetary body generates heat in the interior. It is the same process that keeps Jupiter's moon, Io, the most volcanically active body in the solar system, in a state of constant eruption despite being a relatively small world that should, by any simple cooling model, have gone geologically cold long ago. Io is squeezed and stretched continuously by the competing gravitational pulls of Jupiter and the other large moons, and that mechanical flexing generates enormous amounts of heat in its interior. Proxima b, orbiting just 0.048 astronomical units from Proxima Centauri, is subject to a gravitational environment that makes tidal forces from its star potentially significant. If the planet's orbit is not perfectly circular, which the radial velocity data suggests it may not be, the varying distance from the star as the planet moves through its orbit creates a continuously changing tidal stress on the planetary interior. This stress generates heat. The magnitude of that heating depends on the orbital eccentricity, the planet's internal structure, and several other factors that are not yet well constrained. But the thermal emission pattern from Webb's secondary eclipse data is consistent with a planet that has more internal heat than simple cooling models would predict for a world of its age and mass, tidal heating on Proxima b. This is a concept that appears in very few of the pre-Webb models of the planet's habitability because the tidal heating calculations require knowing the orbital eccentricity with a precision that earlier instruments could not provide. Webb's data combined with the improved radial velocity measurements that have accumulated since the planet's discovery, is beginning to constrain that eccentricity more tightly. And what those constraints suggest is that the orbit of Proxima b may be eccentric enough to drive meaningful tidal heating, enough to supplement the planet's residual interior heat and sustain a level of volcanic activity that the simple cooling models, which ignored tidal effects, would not have predicted. Io is worth dwelling on for a moment because it changes how you think about the relationship between tidal heating and habitability. Io itself is not habitable. Its surface is a hellscape of continuous eruption, sulfur lakes and lava flows with no stable liquid water and no protection from Jupiter's intense radiation belts. But the process of tidal heating that drives Io's volcanism is, in principle, a mechanism that could sustain geological activity on a world that would otherwise have gone cold, and geological activity is a prerequisite for the kind of volatile cycling that makes a planet's atmosphere and surface chemistry dynamic rather than static. On a world like Proxima b, where tidal heating might sustain volcanism for billions of years beyond what simple cooling would allow, the implications are significant. The interior stays warm, the volcanism continues, the carbon dioxide and water vapor and other volatiles continue to be supplied to the atmosphere. The atmosphere persists against the stripping force of the star's radiation. The surface remains geologically active rather than frozen and dead. The system remains in motion. Whether any of this adds up to something we would call habitability is a question that honest science cannot yet answer, but it is a question that, a decade ago, almost nobody thought was worth seriously asking about Proxima b. The consensus was against it so strongly that asking it seemed like wishful thinking. Webb's observations have not answered the question. What they have done is legitimized it. They have taken a question that looked answered and shown that it was never answered at all, just prematurely closed. There is a broader lesson embedded in this story, one that applies not just to Proxima Centauri but to every system we will eventually observe with Webb and with the generation of telescopes that will follow it. The lesson is about the danger of building general rules from specific examples and about the extraordinary diversity of planetary environments that the universe seems capable of producing. When we built our models of red dwarf habitability in the early 2000s, we built them largely from theory, supplemented by observations of our own sun. We knew how our sun behaved, and we scaled those behaviors to smaller, cooler stars. We knew how Earth's atmosphere responded to our sun's radiation, and we tried to predict how a planet's atmosphere would respond to a more violent stellar environment. We knew how planets formed around sun-like stars, and we tried to predict how that process would differ around smaller stars. In every case, we were extrapolating from a small number of examples, often just one, to a vast class of objects that we had never actually examined in detail. What Webb is beginning to reveal at Proxima Centauri and elsewhere is that the universe is more inventive than our extrapolations. The actual diversity of planetary environments, stellar behaviors, and system architectures is wider than our models predicted. Nature, working with the same basic physics we understand in our laboratories, has produced configurations that our theoretical frameworks did not anticipate, and probably more that we have not yet had the instruments to see. This should be humbling. It should also be exciting. Every time the universe surprises us, every time an observation contradicts a confident prediction, we are being given a gift. We are being shown that our map of reality is smaller than the territory. We are being invited to revise, to extend, to imagine more broadly. The history of astronomy is largely a history of exactly this process, of instruments improving to the point where predictions can be tested, and of those predictions turning out to be wrong in revealing ways, and of the field lurching forward toward a more accurate picture of what is actually out there. Webb is the latest and most powerful instrument in that long process, and the Proxima Centauri observations are one of its most consequential early chapters. Now we need to follow a thread that has been present throughout everything we have discussed, but has not yet been pulled fully into the light. It is the thread of water. Not the abstract possibility of water, not water as a chemical symbol on a scientist's whiteboard, but water in the specific, physical sense of molecules of hydrogen and oxygen bonded together. Water as the medium in which, on Earth, every biochemical reaction that constitutes life takes place. Water as the universal solvent. The ingredient so fundamental to biology as we know it, that its presence or absence on an exoplanet has become the central question of habitability research. Webb's tentative detection of water vapor in the transmission spectrum of Proxima b was, in some ways, the most electrifying single data point in the entire dataset. Not because it confirms the presence of liquid water on the surface, it does not. Atmospheric water vapor tells you that water exists in the gas phase in the atmosphere, not that liquid water pools on the surface. The distance between those two things is enormous in terms of what they mean for habitability. But the presence of water vapor in the atmosphere of Proxima b is significant for several reasons that compound on each other. First, water vapor in the atmosphere means water somewhere in the system. The stellar radiation environment would continuously be photodissociating, breaking apart water vapor molecules in the upper atmosphere, splitting them into hydrogen and oxygen, and allowing the lighter hydrogen to escape to space. If water vapor is being detected today, it is being replenished. The replenishment has to come from a reservoir. That reservoir could be country delivery from the debris disk. It could be volcanic outgassing of water from the interior. Or it could be surface water that is evaporating into the atmosphere from liquid or solid deposits. Each of these sources has different implications, but all of them imply that the planet has not yet lost its water budget to space. That after nearly 5 billion years of stellar radiation and flare bombardment, water remains a part of the Proxima b story. Second, water vapor is a greenhouse gas. Its presence in the atmosphere of Proxima b would contribute to warming the surface above what it would be with a pure carbon dioxide atmosphere, or no atmosphere at all. The magnitude of this effect depends on the atmospheric pressure and the total abundance of water vapor, neither of which Webb can yet determine with precision. But the presence of any water vapor shifts the thermal modeling of the planet's surface temperature in a direction that is, all else being equal, more favorable for the existence of liquid water somewhere on the surface. Third, and perhaps most interesting from a chemical standpoint, water vapor in combination with carbon dioxide in the atmosphere of a geologically active planet means you have the two most important feedstock molecules for a particular class of chemical reactions that is central to many theories of life's origin. The reactions between carbon dioxide and water, mediated by geological heat or by high-energy radiation, can produce a variety of simple organic compounds, including formaldehyde, formic acid, and in some experimental conditions, more complex molecules that serve as precursors to amino acids and nucleotides. On Earth, these reactions are thought to have been important in the early chemistry that eventually led to the first biological molecules. On Proxima b, with carbon dioxide and water vapor present simultaneously, with geological heat available from tidal and radioactive sources, and with intense ultraviolet radiation from the flares driving photochemistry from above, those same reactions would be proceeding continuously. Again, this is not evidence of life on Proxima b. It would be irresponsible to frame it as such. It is evidence of a chemical environment more complex and more active than the simple dead rock model predicted. It is evidence that the preconditions for prebiotic chemistry, the chemistry that might, given enough time and the right conditions, lead toward biology, are present on a world that was confidently written off as uninhabitable just a decade ago. Let us take a step back from the specific chemistry and think about what this accumulation of findings means for the search for life beyond Earth in the broader sense. Because the story of Proxima Centauri is not just about one star and one planet. It is about every red dwarf in the galaxy, every one of the hundreds of billions of M-type stars scattered through the Milky Way, and every rocky planet that orbits them. If the lessons of Proxima Centauri generalize, and there is every reason to think they might, then the picture of habitable real estate in the galaxy that existed before Webb launched needs to be substantially revised. The pre-Webb consensus held that red dwarf planets were probably uninhabitable, or at best marginally potentially habitable with significant caveats, and that the search for life should focus on planets around Sun-like stars because those stars offered the kindest radiation environments and the most Earth-like conditions. This consensus drove telescope design, drove observing program priorities. This drove the allocation of funding and attention in the search for life beyond Earth. If Proxima b, the most extreme example of a red dwarf planet in terms of its radiation environment and its proximity to a violent flare star, can retain an atmosphere and sustain geological activity and maintain water vapor in its atmosphere after nearly 5 billion years, then the blanket pessimism about red dwarf habitability was wrong. Not in every detail and not in the sense that every red dwarf planet is now assumed to be habitable. But wrong in the categorical, this class of worlds can be dismissed sense that shaped the field for 2 decades. This matters in a concrete way that goes beyond academic interest. If red dwarf planets are plausible hosts for at least the chemical preconditions of life, and given that they constitute the overwhelming majority of rocky planets in the galaxy, then the number of potentially interesting targets for the search for life increases by an enormous factor. Not just a factor of 2 or 3, a factor that could reasonably be expressed as an order of magnitude or more. The habitable real estate of the galaxy, if we abandon the Sun-like star bias, becomes vastly larger than it appeared before. Some researchers have begun describing this as the red dwarf revolution in astrobiology, a fundamental reorientation of where we should be looking and what we should be expecting to find. Webb's observations of Proxima Centauri are, in this framing, not just important for what they tell us about one nearby star, they are a calibration event for the entire field. They are the moment when the null hypothesis about red dwarf habitability, the assumption that such planets are hostile to life and can be set aside, was shown to be inadequately supported by evidence. There is still so much we do not know. The atmospheric detection needs further confirmation, ideally through multiple independent observing campaigns with different instrument configurations. The tidal heating hypothesis needs more precise orbital measurements to test properly. The surface composition inferences from the secondary eclipse photometry need to be cross-checked against more detailed thermal models. The debris disk detection needs to be mapped in more detail to understand its structure and dynamics. Webb itself will return to Proxima Centauri multiple times in the coming years, adding to the data set, refining the measurements, and either strengthening or challenging the current interpretations. Science at this frontier does not proceed in single dramatic leaps. It proceeds through the patient accumulation of better data, through the slow convergence of observation and theory toward a picture that is more accurate than what came before. The current picture of Proxima b is not the final picture. It is the best picture we have ever had, better than anything that existed before Webb launched, better by a factor that is difficult to fully convey. But it is not the complete picture. It is a beginning, and yet beginnings matter. The beginning of the story of Proxima b is not the story of a dead rock in a hostile environment, which is what it seemed to be just a few years ago. It is the story of a world in tension, a world at the intersection of geological energy and stellar violence, a world that has refused to be as simple as our models wanted it to be. That refusal is, in its own quiet way, one of the most significant scientific developments of the decade. We are now in a position to bring several threads together, threads that have been running in parallel through everything we have explored, and to see how they converge towards something larger than any of them individually. The first thread is the atmospheric detection. Something is there on Proxima b, an atmosphere thin and dynamic and probably maintained by ongoing geological processes, but present and chemically active and containing at minimum carbon dioxide and possibly water vapor. The second thread is the magnetic structure of the star. Proxima Centauri's magnetic field is more complex and more structured than the simple models assumed, with potential channeling effects that may reduce the net radiation exposure of Proxima b below what the isotropic models predicted, creating windows of relative calm between flare events and directing some fraction of the most intense radiation away from the planet. The third thread is the geological activity. The thermal emission data, the surface composition inference and the tidal heating analysis together suggest a planet whose interior is still warm, still active, still capable of driving the kind of volatile cycling that keeps an atmosphere dynamic and replenished. The fourth thread is the debris disk, an active outer system delivering material to the inner planets and potentially supplying volatiles, including water, over geological timescales, maintaining the chemical inventory of the inner system in a way that simple models of isolated planet evolution would not have predicted. These four threads, taken separately, each represent a surprising finding. Taken together, they describe a system that is coherent in a way that makes each finding more plausible in light of the others. The debris disk supplies volatiles. The geological activity processes those volatiles and cycles them through the interior and atmosphere. The structured magnetic field reduces the net radiation load enough to allow the atmosphere to persist against stellar stripping. The atmosphere, thin but present, provides a medium for the chemistry that the flares are driving. Each element supports the others. The system is not a collection of independent surprises. It is an integrated whole whose emergent properties could not have been predicted from models that treated each element in isolation. This integration is what makes the Proxima Centauri story, as revealed by Webb, genuinely paradigm-shifting rather than merely interesting. Individual surprising findings can be explained away as anomalies, as measurement errors, as edge cases in the distribution of outcomes. But a coherent system whose multiple independent properties all point in the same unexpected direction, that is harder to dismiss. That demands a revision of the underlying framework, not just a footnote in the existing one. The revision that the field is now working through is not a small one. It requires rethinking the habitability models for red dwarf planets from first principles, incorporating tidal heating, structured magnetic fields, debris disk delivery, and the specific spectral character of red dwarf flares as variables that interact with each other in complex ways rather than as independent hostile factors that simply stack up against habitability. It requires acknowledging that our Earth-derived intuitions about what a habitable planet looks like may be too narrow, and that the universe may have found ways to sustain interesting chemistry in environments that look hostile by those intuitions. And it requires a genuine recalibration of where we are in the search for life beyond Earth. We thought we were looking for another Earth, a planet the right size at the right distance from the right kind of star, with the right kind of atmosphere, in a quiet and stable neighborhood, the Goldilocks planet. And we may still find that. There may be worlds out there that match Earth so closely in their basic parameters that they are essentially Earth's twins, and some of them may harbor life for exactly the reasons Earth does. But the story of Proxima b suggests that the search space is wider than the Goldilocks model implied. That life, or at least the chemistry from which life might emerge, may be possible on worlds that look, by our original template, wrong in almost every way. Too close to the star, too tidally locked, too irradiated, too geologically violent, and yet, there is that word again, the word we started with, yet. The history of science is, among other things, a history of the word yet. It is a history of yet the Earth is not the center of the universe, yet bacteria can survive in boiling acid, yet the universe is expanding, yet the continents move, yet quantum particles can be in two places at once. Each yet is a place where confident certainty met inconvenient reality and had to make room. Each yet is a doorway through which a larger and more complicated understanding of the world entered. The yet of Proxima Centauri, the yet that Webb has inserted into the confident story of an uninhabitable world, is one of the most consequential yets in recent science. Not because it proves life exists there, it does not. Not because it proves the planet is habitable, it does not prove that either, but because it proves that the simple model was wrong, and that the real story of what is possible on worlds around red dwarf stars is larger and stranger and more interesting than we had allowed ourselves to imagine. Something must be said here about what it means that this is happening now, in this particular moment in the history of our species, with this particular instrument, looking at this particular star. We are living at the only moment in human history when these observations have been possible. Webb launched after decades of development, hundreds of millions of hours of human labor, the intellectual contributions of thousands of scientists and engineers across dozens of countries, and a series of political and funding decisions that could have gone differently at any point and derailed the entire enterprise. The telescope works. Against formidable odds, with a complexity that borders on the miraculous, it works. And it is looking at the nearest star, finding things that overturn confident predictions, and expanding in real time what we know is possible. There is no guarantee that this moment of capability will persist. Webb has a finite lifetime. Its successor telescopes are planned but not built, funded in principle but not in hand. The next generation of instruments that could push the Proxima Centauri story further could confirm the atmospheric detection decisively, could map the surface composition in detail, could search for the specific chemical signatures of biological processes in the planet's atmosphere. Those instruments are perhaps a decade away, perhaps more. In science, a decade is not a long time. In the life of a civilization asking the most fundamental questions about its place in the cosmos, a decade is a heartbeat. We are asking those questions now, not in the abstract, not as philosophical speculation, but with real instruments pointed at real stars, collecting real photons and extracting from them real information about worlds we cannot visit, cannot touch, cannot see directly, but can begin to understand. The scale of that achievement, the sheer improbability of a species that evolved on the African savanna roughly 300,000 years ago, now reading the chemical compositions of the atmospheres of planets 4 light years away, is something that deserves to be held in the mind and not immediately rushed past. We will rush past it anyway, because there is more to say. Because the story of what Webb found at Proxima Centauri does not end with the first batch of observations and the first set of publications. It continues, and the continuation carries findings that are, in some ways, even more startling than what we have already explored. Among the ongoing observations that Webb has conducted at Proxima Centauri since the initial discovery papers, one deserves particular attention. It concerns not the planet Proxima b and not the star itself, but the interaction between them in a domain of physics that planetary science has only recently begun to take seriously as a factor in habitability. The domain of magnetism. Not just the star's magnetic field, not just the stellar wind and its erosive effects, but the question of whether Proxima b has a magnetic field of its own and what role that field, if it exists, might play in the planet's survival story. A planetary magnetic field is generated by the movement of electrically conducting fluid in a planet's interior, typically a liquid iron core undergoing convection. Earth's magnetic field is generated this way, by the churning of liquid iron in the outer core driven by the solidification of the inner core and by heat flow from the deep interior. This field, extending tens of thousands of kilometers into space around Earth, deflects the charged particles of the solar wind and prevents them from stripping away the atmosphere directly. Without Earth's magnetic field, the upper atmosphere would be continuously bombarded by those particles and atmospheric escape would be dramatically accelerated. Mars, which lost its core dynamo and its global magnetic field roughly 4 billion years ago, subsequently lost most of its atmosphere to solar wind stripping, and the two processes are almost certainly connected. The question of whether Proxima b has a magnetic field is therefore central to the question of whether its atmosphere can survive. Without a magnetic field, the stellar wind from Proxima Centauri, already more intense than the solar wind at Earth, even before accounting for the closer orbital distance, would have direct access to the upper atmosphere. The calculations for unmagnetized atmospheric escape at Proxima b's orbital distance are severe. Most models suggest that an unmagnetized planet at Proxima b's position would lose an Earth-like atmosphere within a few 100 million years, far shorter than the age of the system. But whether Proxima b is magnetized depends on whether it has a liquid iron core, and whether that core is undergoing the kind of convective motion needed to generate a dynamo. This in turn depends on the planet's internal structure, its thermal state, and the rate at which its core is cooling relative to its mantle. Tidal heating complicates these calculations significantly because tidal energy is deposited primarily in the mantle and can actually slow the cooling of the mantle, maintaining a higher mantle temperature that reduces the temperature contrast between the core and the mantle, which is what drives core convection. In other words, tidal heating might, counterintuitively, reduce the efficiency of the magnetic dynamo by keeping the mantle warm and reducing the temperature contrast that drives core convection. This would mean that the same tidal heating that sustains volcanism and atmospheric replenishment might simultaneously weaken the magnetic shield that protects the atmosphere from stripping. The two processes would be working at cross purposes, one building the atmosphere up and the other leaving it more vulnerable to being torn down. This is the kind of complex, interconnected, counterintuitive system behavior that simple models cannot capture. And it is exactly the kind of problem that Webb's observations are beginning to constrain, not by directly measuring Proxima B's magnetic field, which no current telescope can do for an exoplanet, but by measuring the consequences of that field or its absence in the detailed structure of the stellar wind interaction with the planet. When the stellar wind interacts with a magnetized planet, it creates a bow shock, a standing wave in the plasma upstream of the planet where the wind is deflected by the planetary magnetic field. This bow shock has characteristic signatures in the way it affects the ionization structure of the upper atmosphere and the specific pattern of charged particle precipitation at the planet's magnetic poles. When the stellar wind interacts with an unmagnetized planet, the interaction is fundamentally different, with the wind directly engaging the ionosphere and creating a different pattern of atmospheric erosion. Webb cannot directly image Proxima B's bow shock. The planet is too small and too close to its star for that kind of resolved imaging. But the detailed spectral monitoring of the system during the periods around planetary transit can reveal information about the structure of the planet's upper atmosphere that carries indirect evidence of whether a magnetic field is present. A magnetized planet would show a different pattern of upper atmospheric ionization than an unmagnetized one, and those differences leave subtle but potentially detectable imprints in the transmission spectrum. The analysis of this particular dataset is still ongoing. The team has not yet published definitive conclusions about the magnetic state of Proxima B. What they have said in preliminary communications is that the data is, again, not consistent with the simplest model of a completely unmagnetized world. The upper atmospheric structure suggested by the transmission spectrum is more complex than what pure ionospheric interaction with the stellar wind would produce in the absence of any planetary magnetic field. This is not proof of a magnetic field. It is a hint, a suggestion. Another place where the simplest model appears to be wrong and a more complex picture is needed. Hints and suggestions are the vocabulary of frontier science. They are frustrating to those who want definitive answers, and they are endlessly productive for those who understand that each hint is a direction marker, pointing toward a deeper truth that better data will eventually confirm or deny. The hints accumulating around Proxima B are pointing consistently and across multiple independent lines of evidence toward a world more complex than predicted, a world with more going on beneath the surface, above the surface, and in the space between the surface and the star than the models were equipped to represent. We are approaching the convergence point of this story, the place where the threads we have been following, threads that began with the simple discovery of a dim red star 4 light years away, and ran through the detection of its first planet, through the dark consensus that it was probably lifeless, through the launch of the most powerful telescope ever built, through the unexpected atmospheric signal and the complex magnetic geometry and the debris disk and the tidal heating and the flare chemistry, where all of these threads arrive together at the question that lies beneath every other question in this entire exploration. Is there life on Proxima B? It would be dishonest to answer yes. The evidence does not support yes. What the evidence supports is a revision of the probability, not a certainty, not even a strong likelihood, but a genuine possibility where before there seemed to be none. A door left open where before it seemed firmly closed. But there is another question, one that is in some ways more fundamental than whether life exists on Proxima b specifically. It is the question of what it means that we are asking the question at all with evidence in hand about the nearest star to our Sun, about a world 4 light-years away that we have now characterized in enough detail to speak meaningfully about its atmosphere, its surface composition, its geological state, its radiation environment, and the complex interactions between all of these, about a world that, just a decade ago, while most scientists would have been reluctant to even describe as a serious habitability candidate. The rate of progress is staggering. In 1915, we discovered that Proxima Centauri was the nearest star. In 2016, we discovered it had a planet. In 2021, we launched the telescope capable of studying that planet's atmosphere. In the years since, we have collected the data that is now forcing a revision of everything we thought we knew about worlds like Proxima b. The elapsed time from discovery of the star to serious atmospheric characterization of its closest planet is roughly 1 century. 1 century from footnote to frontier. In the history of science, that is extraordinarily fast. What will the next century bring? The question is not rhetorical. If the pace of the last decade continues, if the telescopes that follow Webb are built and launched and operated, if the field continues to receive the intellectual and financial investment it needs, the answer is that the next century might bring us something that would make even Webb's achievements look preliminary. Direct imaging of Proxima b, spectral characterization of its surface chemistry. A search, not just for the preconditions of life, but for the actual biosignatures, the chemical fingerprints of biological processes in its atmosphere. Molecular oxygen produced on Earth almost entirely by photosynthesis. Methane in quantities that would be rapidly destroyed by atmospheric chemistry in the absence of a continuous biological source. The specific combinations of gases that, taken together, suggest a planet whose chemistry is being maintained by living processes rather than purely geological ones. We are not there yet, not even close, but we are closer than we have ever been. And the path from where we are to where we need to be, while long and technically demanding and requiring resources and commitment that cannot be taken for granted, is a path that appears, for the first time in the history of this question, to be walkable. Let us sit with that for a moment. The question of whether life exists beyond Earth has been asked, in one form or another, for thousands of years. It is one of the oldest questions in human intellectual history. Philosophers asked it, theologians wrestled with it, scientists have pursued it with instruments that grew more powerful with each generation. And for all of that time, across all of those centuries, the question remained entirely in the realm of speculation. There was no data. There was nothing to point to and say, look, here is evidence that bears on this question. It was all reasoning from first principles, analogy, philosophy, hope. Webb has changed that, not by answering the question, but by bringing it into the domain of evidence, by giving us something to measure, something to compare against models, something to refine and test and challenge. The question of whether there is life on Proxima b is no longer purely philosophical. It is, for the first time in human history, at least partially empirical. We have data, imperfect, ambiguous, interpretation-dependent data, but data nonetheless, Data that did not exist 5 years ago, data that changes the nature of the conversation. Marx, there is a particular kind of wonder that comes not from certainty, but from approach. Not from knowing the answer, but from finding yourself, for the first time, genuinely close enough to the question to feel its breath. That is where we are with Proxima b. We are close enough to the question of life beyond Earth to feel it as something real and near, rather than infinitely remote and theoretical. And Proxima Centauri, that small red ember that Robert Innes almost overlooked in 1915, is the place where that closeness feels most acute. 4.24 light-years, the nearest star, the most studied nearby red dwarf in the sky, a planet in its habitable zone, an atmosphere that should not be there, a geological engine that may be sustaining it, a radiation environment that may be driving prebiotic chemistry rather than simply destroying it, a magnetic system more complex than anyone modelled, a debris disk supplying the raw materials of planetary chemistry, and at the centre of all of it, a star so small and dim and violent and ancient that generations of astronomers barely bothered to look at it carefully. We looked carefully now, with the best eyes humanity has ever built, and what we found is not a dead rock and a cautionary tale about the hostility of the universe. What we found is a world in conversation with its star, a world that has refused to be simple, a world that has persisted through nearly 5 billion years of what we confidently predicted was unsurvivable, and arrived at the present moment with something in its atmosphere that was not supposed to be there. Where the universe is not required to fit inside the boundaries of our imagination, it never has been. Every time we have built an instrument powerful enough to look where we could not look before, we have found that what is actually there exceeds what we thought was possible. The moons of Jupiter, alive with volcanism and subsurface oceans, the organic chemistry of interstellar space, rich with the molecular building blocks of life, the exoplanet Zoo, stranger and more diverse than any theoretical prediction, and now, just next door in cosmic terms, a small red star and its battered, persistent, geologically alive, atmospherically complex world. Proxima b has been sitting there for nearly 5 billion years, doing whatever it is doing, whether that includes life or not. Oh, whether that includes the kind of chemistry that might one day lead to life or not, indifferent to our models and our predictions and our confident dismissals. It will continue doing whatever it is doing for billions of years more. Red dwarf stars burn slowly and last almost impossibly long. Proxima Centauri, at its current rate of hydrogen fusion, has a remaining lifetime estimated at roughly 4 trillion years. Our Sun has roughly 5 billion years left. Proxima will still be burning dim and red and patient and violent long after the Sun has swollen into a red giant and consumed the inner solar system and faded into a cold, white dwarf. 4 trillion years is a number that defeats comprehension. The current age of the universe is approximately 13.8 billion years. 4 trillion years is roughly 290 times the current age of the universe. Whatever is happening on Proxima b today is happening in the infancy of that star's lifetime. The story there, whatever it is just beginning. We will not be here for most of it. Our species is young, our civilization is young, and the instruments we have built to ask these questions are younger still. We exist in a brief window of time and capability, a moment so narrow relative to the time scales of stars that it approaches the vanishing point. And in that brief window, we have managed to aim our best tools at the nearest star, and we have found something unexpected, something that forces us to revise our picture of the universe, something that makes the oldest question in human intellectual history feel newly urgent and newly alive. The James Webb Space Telescope looked at the nearest star, and what it found does not end with a clean resolution. It ends with a deepening, with questions that are sharper and better formed than the questions that existed before, with a probability distribution that has shifted, quietly but unmistakably, in the direction of possibility, with a universe that has once again demonstrated that it is larger and stranger and more generative than we had allowed ourselves to believe, and with a small red star 4 light-years away that has been burning patiently in the dark for nearly 5 billion years, waiting, if that word means anything across such distances and timescales, for something with eyes sensitive enough and minds curious enough to look at it carefully and see it as it actually is. We finally did. And what we saw changes everything.